So notes part 2 of related rates. Our test is next Tuesday. I looked yesterday and made sure it's a little bit shorter than, or significantly shorter than a block day test, because it's a shorter time, so it'll be okay time-wise. But the main thing I wanted to say before we got started was these last 2 examples we're about to do are the last new notes that we'll give before the test. So review, test. So we got some review time coming up. All right, those last 2 examples. In the above example, the 13-foot ladder leans against the wall, making an angle with the flat ground. Okay, so that 13-foot ladder, now there's an angle with the ground. The ladder is now falling down the wall. I guess we can stick with our x and y here, at a constant rate of 0.5 feet per second. Okay, so something is 0.5 feet per second. Falling down the wall at 0.5 feet per second. So what's 0.5 feet per second in terms of my variables? dy dt. And I left out something kind of important in there. Anybody see a mistake that I've intentionally done? What's not quite right about that statement? And this is what will get people, because it's not explicitly said in the statement, so you got to read it carefully. No, it's feet per second. There's not a mistake in the problem. There's a mistake in what I've written here.
Negative?
Why is it negative? Because going down. So dy, or y is shrinking, so the change in y is negative. Now, it's possible that we might have figured that out later. A lot of times, the negative stuff can make sense. In fact, well, we'll hold that thought. At what rate is the angle between the ladder and the ground changing? So find d theta dt when the top of the ladder is 5 feet from the ground. So when y equals 5. Okay, so as this ladder slides down the wall, that angle, is it getting bigger or smaller? Smaller. So I think d theta dt should be negative. So again, that's one spot where if we get a positive there, we would have to go back and find our mistake. And it might have been that right there. Okay, so I need to come up with a formula that uses the variables that I've got. Need a formula with my variables. So the variables are, no mention of x was made, so I'd like to avoid using x if possible. Y is involved and theta is involved. So can you think of a relationship that involves theta and y? Joe?
Arc sine of y over 13 equals theta.
Arc sine of y over 13 equals theta. Yes. Except that we don't know the derivative for arc sine. So true statement, we will learn the derivative for arc sine later, but we don't know it now. So that is true, and that's actually maybe a good one, because then we'd have d theta dt by itself already. But we don't know the derivative for arc sine. So let's write it instead as a sine problem. So you're on the right track. I do know the derivative of sine. So let's see, sine of theta is y over 13. That I know the derivative for. That's a very easy derivative. The derivative of arc sine is not easy. Yeah, that's a pain. We'll get there later. So derivative of sine theta, but I want t to show up, so I need to take a derivative with respect to time. So what's the derivative of sine of theta? Cosine of theta. Good, d theta dt. And that's a 1/13 y, so I'm going to write it as 1/13. Derivative of y is dy dt. Okay, find d theta dt. Got it. When y equals 5. Okay, that doesn't directly help me here yet, anyway. Dy dt I know. So I need the cosine of that angle when it said when y is 5. So theta 5, 13. Cosine of the angle is adjacent over hypotenuse. What's my adjacent side? It's the same triangle from yesterday. 12, 5, 12, 13. So the cosine of that angle is 12/13. So 12/13 is the cosine of the angle. D theta dt is what we're looking for. 1/13 times negative 0.5. This? Because right here, y over 13, that's the same thing as 1/13 y. So the derivative of 1/13 y is 1/13 dy dt. Probably the first thing I do is multiply both sides by 13, and those go away. And then divide both sides by 12. D theta dt is negative 0.5 over 12. That's kind of a weird answer, but we are okay with weird answers. Multiple choice, that'd be 1/2 over 12, so that'd be 1/24. 1/24. Negative 1/24. Oh, indicate units of measure. Well, again, we don't really keep up with units through the problem. We just hop on at the end and say, what is theta measured in? Well, I heard degrees and radians. So, which one is it? In all of our problems, for all of this stuff to work, it's got to be radians. So radians per time is in seconds, radians per second. But probably that key step in there was writing an equation that involves your variables. Sometimes they give it to you, other times you have to come up with the equation on your own. Number 6. I don't see an equation, so we'll have to come up with the equation on our own. A 6-foot tall man walks at a rate of 5 feet per second toward a 16-foot tall light pole. Okay, so there's my light pole, 16 feet tall. The man is 6 feet tall. When the man is 10 feet from the base of the pole, I'm trying to draw this like sort of to scale. Not my man, he's not to scale of anything, but so he's 6 feet tall. When he's 10 feet away, at what rate is the length of his shadow changing? What? Right, there's his shadow right there. Well, if I was really good, I'd draw his shadow on the ground. Thanks. Okay, let's see if I've got all that picture drawn right. 6 foot tall man walks at a rate of, so he's walking this way toward the light pole at 5 feet per second. Somebody should do the math and convert that to miles per hour to figure out how fast he's really walking there. 16-foot tall light pole. When the man is 10 feet from the pole, at what rate is the length of his shadow changing? So I'm calling this his shadow, and what I want to find, so what am I trying to find in terms of my variables? What rate? So I know it's d dt. Length of his shadow I've called s. So I want to find ds dt. Okay, these problems are good because there's not a formula to memorize. You have to look at the problem and figure out a formula. From your J's in geometry. There's similar triangles in here. Right, those triangles are similar. And so we can do some ratio stuff. And on all of these problems, you want to grab as many constants as you can. So 6 and 16, those aren't changing. So 6 to 16 equals, so that's orange triangle to green triangle, orange over green is 6 over 16. Well, what about orange over green for this side? What's the orange length down here? S, for sure. And then, I said this is 10, but that 10 is changing, so I better be careful. I don't want to say the whole length is s plus 10, because it's not always s plus 10. That 10 is changing, so I need to call that something else. It's changing, so I got to call it a variable. Yuck. Let's call it x. So s over, what's the length of the green triangle? Be careful. It's not x. X plus s. It's both of them. Trying to find ds dt. Okay, well ds dt will show up if I take a derivative here. What about x? If I take a derivative, dx dt is going to show up. On a related note, I've got 5 feet per second here. What's changing at 5 feet per second in terms of my picture? X is, so that's dx dt. Anders, is it positive or negative? Is x growing or shrinking? Shrinking, so that's a negative 5 feet per second. So he's walking 5 feet per second, that's his speed, but as he's walking that fast, this x distance is shrinking at 5 feet per second. Okay, so I think I have everything I need. If I take a derivative right now, I would need the quotient rule. Yuck. Boo. Correct. I don't want to. So instead, let's cross multiply. Let's do algebra first and get rid of the denominators altogether. So 6s plus 6x equals 16s. Well, now I'm on a roll with my algebra. Let's move the 6s over. So 6x equals 10s. I think I'm out of algebra steps. But derivatives should be easy now. Take a derivative with respect to time. So what's the derivative of x with respect to time? dx dt. So 6 dx dt. And then 10, what's the derivative of s with respect to time? ds dt. Okay, so 6 times dx dt is negative 5. ds dt is what we're looking for. So negative 30 equals 10 ds dt. So ds dt is negative 3. So his shadow is getting shorter. Does that make sense for this problem? Right? If he's 6 feet tall, so he's not like walking along, his head's not following this path. Like a second later, he's over here. And so yeah, his shadow is getting shorter, so that makes sense. It didn't ask for units, but s is feet, time is seconds, so his shadow is getting shorter at 3 feet per second. Ratios of similar triangles. Yay, geometry. But hey, as far as geometry goes, that's a pretty simple part of geometry, right? Like just orange to green equals orange to green. And then do some algebra first to clean things up. Alright, so perhaps now you know why we spend a couple days on this, because there's all sorts of equations, like all your geometry equations, all your algebra equations, all your calculus, some of the computational stuff, and fractions. So there's a lot going on, but that's why we have time to work on it. So officially today's assignment is 6 through 17, but like in class together with the group thing in a minute, we're going to do 6, 7, 8, and 9. So you should have those done before you leave, and then I think we'll still have time for you to work on the rest of them. And then you got a weekend and 2 days to work on the review worksheet, so time isn't the issue. Understanding might be, figuring it out might be, but I think we'll have time.